All right, so let's see if we can figure out exactly how to use sum a geometric series. So we're going to be interested in the sum constant times 1 plus r squared plus r cubed, and so on. And we'll start off by thinking about partial sums. So the nth partial sum is equal to constant times 1 plus r squared. And then if we want to add up n terms, the last power will be r to the n minus 1. And that's due to the fact that we started with this one, which you could think of as r to the 0. So we have a first power, we have a second power, all the way up to n minus 1. That's n minus 1 terms. And then we include the 0. We get a total of n. Okay? All right, so that is Sn, the nth partial sum of the geometric series. Okay? And what we would like to do is figure out, could we actually simplify that expression? Is there a nice way to write this? And so we're going to try a clever little trick. We're going to multiply this quantity by 1 minus r. All right, so we just multiplied by the same thing on both sides. And now, what I'd like to do is I'd like to FOIL this out. And I'm going to leave the c alone outside. That's just going to stay where it is. And notice when I multiply 1 by the second term, I'm just going to have 1 plus r to the 1 plus r squared, and so on. I'm going to have exactly this original expression once. Minus, and then for the second term, when we take into account the r, we're going to have r times each of these. And so I'll write this out as follows. We'll have minus r, and that comes from the r times 1, and then we'll have r times r. And that pattern is going to continue. And basically what we're going to get is the same terms, all with a power that's 1 higher than what we had when we multiplied by 1. Agreed? All right, so we've FOILed this out. 1 times the second term is on top. R times the second term is on bottom. And notice there's a lot of terms that are going to cancel out here because we have an r to the 1 minus r to the 1. So those cancel. And r squared is going to cancel. And in fact, r to the n minus 1 is cancel, and all of the ones in between. And so the only ones that are going to stick around are the 1 and the r to the n. And so this has got to simplify down to just c times 1 minus r to the n. And if we rearrange that just a little bit, we can solve for Sn. And now we have a nice expression for the partial sums. Okay, so let's remember where we were headed. We're trying to describe this sum. And what we did is we started by identifying the formula for the partial sums. And now we found a new formula that is a little simpler, and it doesn't have an infinite sum in it. Okay? So the total sum, the sum of the geometric series, must be equal to the limit as n goes to infinity of Sn. Meaning if I want to figure out what happens when I add up an infinite number of things, I can take that finite number of things, Sn, and I can just keep adding more and more terms and let the number of terms go to infinity. So if we could evaluate this limit, we could figure out exactly what the sum is going to be. Now, this limit, most of the terms don't actually depend on n at all. So we can actually simplify this quite a bit. We can FOIL out. We can write this as c over 1 minus r minus c times r to the n over 1 minus r. And the only thing that has an n in it is that r to the n term. And so what we'll have is 1 minus r minus c over 1 minus r times the limit as n goes to infinity of r to the n. So I've just pulled out the parts that were constant using our sum and constant multiple rules for limits. And so all we need to be able to do, excuse me, is evaluate this limit. Well, let's think about that for a second. That's just the sequence that we studied earlier. That just comes from the geometric sequence. And we, in fact, already know that this quantity is going to approach 0 if r is between -1 and 1. I encourage you to go back and watch some of the videos from chapter 10.1 if you don't remember that, but we did actually argue that earlier on. And if r is greater than 1, you can show that this is going to go to infinity. And if r is less than -1, you can show that the limit does not exist. And that just leaves a couple of cases. R equals 1 and r equals -1. Well, if r is 1, what happens if you take 1 and raise it to larger and larger powers? Well, nothing, right? You just get a value of 1. But notice something. If r was equal to 1, we would have a problem here. We'd be dividing by 0. So that's going to be a special case. We're going to have to think about that carefully. If r is equal to -1, then we're taking -1 and multiplying it by higher and higher powers. Well, as you multiply -1 by itself by larger and larger numbers of times, you're going to go from negative to positive to negative to positive to negative to positive, -1 plus 1, negative plus 1 plus 1, and so on. You're going to keep alternating back and forth, and so that's not going to approach anything, and so we would say that that does not exist. So what does that mean? All right, to put everything together, we can say that the sum, which is the limit as n goes to infinity of the partial sums, is equal to, well, if r to the n is approaching 0, we're just going to get c over 1 minus r. If r is between -1 and 1, and another way of writing that would be if the absolute value of r is less than 1. And then what we'll see is for all of the other cases, it is going to diverge because this limit is not going to exist or will indeed be dividing by 0. And if you think about the special case where you're adding up 1 multiplied by itself over and over again, you'll see that it does indeed diverge. Okay, so our geometric series, and I'll remind you what that is the sum from n equals 0 to infinity of c r to the n. It converges if the ratio is less than 1 in absolute value, and it diverges if the absolute value is greater than or equal to 1. All right, this is one of the more important results that we will talk about in this unit on sequences series, so you're definitely going to want to commit that result to memory. And in the next video, we'll take a look at a few examples where we apply that to the applied problems from the previous video, the ones involving the epidemic, the one involving the $1,000, and the one involving the ball bouncing up and down.